Hi everyone, my name is Nishant Roy, and I'm here today to talk to you about heap optimizations for Go systems. To start off, here's a little bit about me. I work in the ad serving architecture team over here at Pinterest. I've been here for about 3 years, and I've spent a fair bit of the time working in memory optimizations for our Go systems. I graduated from Georgia Tech back in 2017 and moved out of San Francisco pretty soon after. Two of my favorite things in life are brunch and basketball, both of which are available in abundance in the city, so it's a pretty great place to be. Okay, let's dive right in. Let's start with a quick intro to memory management and how it works in Go. So at a high level, memory management refers to allocating memory for a program upon request, and then freeing it up for use by other programs once it's no longer needed. Go in particular does not require users to perform any manual memory management, which means that users do not need to manually allocate and clear memory. Both these functionalities are abstracted away from the user to simplify usage and to minimize the chance of any memory leaks. The Go garbage collector runs every time that the heap hits a certain target size. By default, this means that a new GC cycle is triggered whenever the heap grows by 100% since the last collection, although this target size is configurable through an environment variable. Go GC uses a tricolor algorithm for marking objects. So it divides the objects in the heap into 3 different sets while it's scanning the heap. The first set is white, which means the objects are collectible, that they are no longer in use in memory. Black objects are the second set, which are not collectible since they are definitely in use in memory. And the third set are gray objects, which may be collectible, but they have not been determined yet. This tricolor algorithm allows GC to run concurrently in Go with the main program without any stop the world pause. So next up, let's take a look at how GC may impact performance for our main program. Go garbage collection aims to utilize no more than 25% of CPU resources, and ideally this should minimize the impact on program performance and latency. However, when memory pressure is high, more CPU resources may be used for garbage collection, which can severely hinder the performance of the main program. When the rate of memory allocation in the program is high, Go GC steals Go routines from the main program to assist with the marking phase of GC. This is done to ensure that the rate of memory allocation is not greater than the rate of memory cleanup, because stealing away these Go routines means that the main program, known as the mutator, cannot allocate more memory than is being cleaned up. This prevents the heap from growing to be very large, and it's a protection built in to prevent problems such as out-of-memory crashes. So the next thing we need to know is what actually causes GC pressure. In order to determine what memory is ready to be cleaned up, the Go garbage collector needs to scan every single object in the heap to determine if it's still in use or not. So as the number of objects in the heap grows, so does the amount of time spent scanning the heap and the amount of resources spent on garbage collection. So what does the heap actually contain? So in general, there are 2 areas for memory allocation in computer programs, the stack and the heap. The stack is a special area of the computer's memory which stores temporary variables created by a particular function. And since each function stack is cleared once it's done executing, if these variables were not moved elsewhere, we would have no way of accessing them later on. And this is where the heap comes in. The heap is a more free-floating memory region, which is used to store global variables or variables that are referenced outside the scope of a function. So how does Go determine what goes in the heap? Go uses a method called escape analysis, similar to many other programming languages, to determine what goes in the heap versus the stack. Escape analysis is beyond the scope of this talk, but at a high level, it does exactly as mentioned before. It looks to see if a particular object is only referenced within the scope of a specific function call. And if so, we know it can be allocated to the stack for that function. However, if an object is needed outside of that function, it likely needs to be allocated to the heap. Things are a little more nuanced, but that is a very basic high-level explanation. So the next thing we need to know is how do we determine if GC is really the problem? If we are experiencing some sort of performance degradation, how do we know that garbage collection is causing it? In part, we do need to rely on intuition, and intuition can help guide us in the right direction. So GC pressure typically manifests itself in the form of high tail latency. And tail latency refers to when we have a small percentage of requests to a system that result in very slow responses. We typically talk about latency as percentiles, and high tail latency refers to abnormally high latency values for high percentiles, such as P99. If you observe such symptoms, then GC pressure could be your root cause, especially if you know that your program does have high memory usage. So in order to confirm your hypothesis, you can leverage the Go runtime environment variable GODEBUG. By setting GODEBUG equals GCTrace equals 1 when running your program, you can force your program to output debug logs for each GC cycle. And these debug logs detail the time spent on the various GC phases and give you a bunch more information. So if you find that your system's performance metrics align with the times of the GC cycles, so for example, if you are seeing a high spike in latency every 3 seconds and that aligns with the time of GC cycles, there's a good chance that garbage collection is the cause of the performance regression that you're witnessing. So here's an example of what GCTrace's output looks like with an explanation of the various components. And credits go to Ardent Labs here. If you were to Google GCTrace Ardent Labs, you'll have a great breakdown of how this works. So taking a quick look, we see that GCTrace gives us a lot of useful information, like how many GC cycles we've had so far, how much of our program's total CPU has been spent on garbage collection, how much wall clock and CPU time were spent in the various phases of GC, and what our memory usage looks like before and after the objects were marked. I'm not going to go in too deep into the various aspects here, but if you check out Ardent Labs' blog post, there's a great explanation. What I typically find the most helpful is to let GCTrace run and add a new background thread to print out certain key system metrics that I care about, such as latency, P99 latency, etc., on a regular interval. And then I look for correlations between when the GC cycles occur and when the latency degradations occur. This kind of helps me determine if a system is suffering from GC pressure. So now if we do know that GC pressure is our problem, how do we then take a look at our heaps usage? How do we profile the heap? Go comes with many built-in tools to investigate such performance issues. And the two that I have found particularly helpful are the memstats and pprof packages. These allow us to see stats around memory management and also to visualize profile data for various aspects of the system, such as CPU usage, heap usage, etc. So first off, let's take a look at memstats. The runtime.memstats library exposes statistics about the system's memory usage, garbage collection stats, etc. We can use this library to monitor the total number of objects on the heap, which, as we discussed earlier, is closely tied to the amount of resources needed for GC. We can also use this metric as our indicator for success. That is, once we start to make heap optimizations, we would expect this metric to drop. The memstats docs provide a clear explanation of the various statistics exposed by the library. Here are a few metrics related to heap usage that may be useful. So the number of allocated heap objects, the total number of bytes in use on the heap, and the total amount of memory that our program has obtained from the OS. But please refer to the Go docs linked here for a much more detailed breakdown of all the other metrics. So here's an example of how memstats may be useful. We can put together a quick program to demonstrate it. In this program, we perform some heavy allocations in a loop, then force a garbage collection cycle, and print out some of the stats exposed by the memstats library to understand how the system is performing at various times. As we see here, when we run the program, we can see how the memory stats change over time, and we can use a very similar method to understand the memory behavior for more complex systems. The second package I wanted to talk about was pprof, and the pprof package allows us to visualize several system profiles, including CPU, memory usage, etc. Here, we're focused specifically on the heap profile. The heap profile tool comes with several options to investigate specific aspects of the heap. For example, if we're looking into out-of-memory issues, we may be more interested in the actual amount of memory used. But in our case, since we know that GC pressure is tied closely to the number of objects in the heap, that profile is a lot more interesting to us. So the first command shown here can be used to download the profile data to your machine. And it also puts you in an interactive command line to start visualizing the data. And by running the help command, you can see all the available options. So the way you need to set up Go pprof is clear from the pprof docs. You simply need to import the pprof package and run an HTTP server, which sets up various HTTP handlers allowing you to access this pprof debug data. So my personal preference to visualize the profile data is to run the second command listed here in a new terminal to open the profile data in an interactive web browser. Let's take a look at a couple of the examples of what sort of visualizations the web browser provides. So here's one of them. You can see the number of objects in use by various call stacks here, which can be helpful in narrowing down problematic code. The other option is to use the flame graph view. So you can visualize the heap usage as a flame graph, and this flame graph is interactive. So if you click on any bar, it focuses in on that specific call stack. And the width of a call stack here is based on the number of heap objects it allocates, which means that wider call stacks are using a higher number of heap objects, which allows you to hone in a lot easier and a lot faster. One thing to keep in mind is that this does represent the heap objects at the time the profile was captured. So it's possible that you may have a red herring here that doesn't actually represent the true problem. So just make sure to run this heap profile a few times to confirm that what you're looking at is the real problem. So the other thing that pprof provides is a pretty great CLI tool. So once you've identified some functions that you know or you think are contributing a large number of objects, you can go back to the CLI that we entered when we first pulled the profile data. In here, we can use the list command to see how many objects are allocated by each line of a method. So if you run list followed by your method name, it shows you this line-by-line breakdown to print out the data in your terminal. In this case, we can see that lines 233 and 237 are clearly creating a large number of new objects, causing a lot of heap allocations. While line 241 adds the objects to a map, which also causes a large number of heap allocations. So now we know exactly which part of our code is problematic. How can we go on to limit the impact of GC? So as we previously discussed, garbage collection becomes really expensive when we have a large number of heap objects or when the rate of memory allocation is high. So if we can lower the number of objects in the heap or reduce the rate of object allocation, in addition to this, if we can optimize our data structures for minimal memory usage, we can do a lot to mitigate the impact of GC, make it more lightweight, and leave more resources for our main program. So let's look at some ways to do that. Firstly, let's look at reducing long-living heap objects. Rather than having objects living on the heap, they can be created as values rather than references on demand. For instance, if we need some data for each item in a user request that we need to process, rather than pre-computing this data and storing it in a long-lived map, we can compute it on a per-request basis to reduce the number of objects in the heap. If we have a reference to an object and the object itself then contains further pointers, these are also all considered individual objects in the heap, even though they may be nested. And by changing these nested values to be non-pointers, we can reduce the number of objects to be scanned. Finally, a key thing to remember is that strings and byte arrays are treated as pointers under the hood, and each one therefore is an object in the heap. So if possible, it's best to try and represent these as other non-pointer values, such as integers, floats, time objects for dates, and so on. One thing to keep in mind here is that this is very specific to each use case. If you are constantly creating a lot of values on demand, this can actually cause further GC problems. So it's really important to understand your use case and adapt accordingly. Even with nested pointers, it's possible that if these pointers, if you convert them to values and they're being passed around a lot, these values would need to be copied every time they're passed around, as opposed to with pointers, they're passed by reference. So just making sure that you understand the nuances of your system can be really helpful. But these are some tips to reduce the number of long-living heap objects, which can help reduce your GC pressure. So next up, let's take a quick look at the impact of removing strings. So looking at this example that we looked at before, the create catalog map method, if we replace our map key, which in this case currently is a string, if we replace the map key with a struct instead that contains the three IDs here, the product ID, the seller ID, and the catalog version, we see that the number of heap objects actually drops about 26 million. So that's a 20% reduction in the heap objects, which means we can vastly reduce the amount of time and resources spent on garbage collection. So the next thing we can do is to reduce the rate of allocation. So if your program tends to create a large number of short-lived objects in bursts, you may be able to benefit from object pooling. which can be used to allocate and free memory blocks manually. By doing so, this can reduce the number of GC cycles needed since the pool retains these objects for a longer scope, so we don't need to keep allocating and cleaning up these objects. One thing to note is that object pools can cause memory leaks if not used properly. So this is only recommended if you know what you're doing and if you're really confident that this is the problem in your system. Next, it's really important that you make sure to clean up unused data fields. In particular, we have basic types in Go which have default values. For example, a Boolean defaults to false, an integer defaults to 0, etc. So if you do have unused fields in your data structures of these types, they are still consuming memory. So an unused field is one that is just no longer being read, no longer being used to serve any requests, or not being logged offline. Removing such a field should be a no-op. By removing these fields, we lower the program's memory usage and also have the added benefit of making the code more readable and easy to understand for future users. So here we can see that by removing 4 of our fields, we're able to reduce the size of our object from 64 to 40 bytes. And as you can imagine, if you have a large number of objects that you're storing, this could be a very significant optimization. So one more thing for us to keep in mind as we're looking at our data structures is how the Go memory allocator actually works. And it does not optimize to minimize the memory usage. In this case, as you can see, we have 2 objects with identical fields, just ordered differently. The objects are allocated 1 field at a time, and in this case, for the bad object, in order to respect word alignment, the Go allocator adds padding to the data in memory. But by carefully rearranging the fields, we can reduce the amount of padding needed. And here we can see that just rearranging them lowered our memory usage by 40%. So overall, by pruning the unused fields and rearranging the rest, we went from a size of 64 bytes to 24 bytes, which was almost a 62% improvement. In a large-scale system with thousands or millions of such objects in use in memory, this simple method could vastly reduce our memory usage and improve our performance. So in summary, the Go garbage collector is pretty great, and it's highly optimized for most use cases, and most developers do not need to worry about the details of its implementation and its performance. However, for some heavy use cases, the garbage collector can actually cause significant impact to your program's performance. And having an understanding of how the garbage collector works, how memory management works, and some of the built-in tools can be extremely vital to understanding and solving the problem. From there on, as we discussed, we have several optimizations available to improve our system and improve our performance. That's all for today. Thank you so much for listening. Hopefully this helped you understand how garbage collection works in Go and how you can go about optimizing your system to minimize the impact of garbage collection. Once again, I'm Nishant Roy from Pinterest, wishing you the very best. Thank you.